Digital maps are now essential tools in daily life, helping us navigate cities, plan routes, estimate travel times, and explore new places. But behind this seemingly simple interface lies a highly complex system involving real-time data ingestion, geospatial computation, efficient rendering, and distributed infrastructure. In this design exercise, we'll walk through how to build a simplified version of Google Maps. The goal is to support core features, displaying maps, tracking user location, computing navigation routes, and showing estimated times of arrival, ETA. While advanced features like Street View or AR overlays are out of scope, even this minimal functionality requires a thoughtful system design. To start, we must understand key requirements. How many users are expected? How large is the geographic data? Do we consider traffic and different transportation modes? These questions shape the system's scale and architecture. Next, we'll explore the fundamentals: how to represent locations, latitude and longitude, how to project 3D Earth data onto 2D screens, and how to render maps using tiles for scalability. We'll examine how client devices send location updates, how those updates are stored and processed using technologies like Cassandra and Kafka, and how navigation paths are computed using graph algorithms such as Dijkstra or ASI. Finally, we'll discuss delivery: map tiles served via CDNs, real-time updates pushed via WebSockets, and optimizations like using vector data for rendering. This high-level walkthrough highlights how to architect a modular, scalable, and responsive system for digital mapping, balancing performance, accuracy, and user experience. The problem is to design a simple version of Google Maps with navigation, ETA, and map rendering. Here are some good requirement questions to ask. What's the DAU? How large is the road data? Do traffic conditions matter? How about different travel modes?
Let's start with the foundational concepts behind any digital map system. Positioning system. Everything on the map is grounded in real-world coordinates, specifically latitude and longitude. These two values represent a point on the Earth's surface, allowing us to pinpoint and track locations globally. Map projection. Because the Earth is a 3D sphere, but our screens are 2D, we need a way to translate 3D geographic coordinates onto a flat surface. This is where map projections come in. Common ones include Mercator or Web Mercator, which preserve shapes and angles for easier navigation, but introduce distortion, especially near the poles. Map rendering, tiling. Rendering the entire world at once would be too heavy and inefficient. So maps are broken into tiles, small square images typically 256 x 256 pixels. Depending on the zoom level and user's viewport, only the necessary tiles are loaded. This allows for fast, scalable rendering and smoother user experience. Navigation algorithms. For route planning, we rely on navigation algorithms such as Dijkstra's or A, which computes the most efficient path from a start to an endpoint based on road networks, traffic data, and user preferences. Hierarchical routing tiles. These are optimizations used in route computation. The idea is to split the world into a hierarchy of tiles, where each tile summarizes routing information at various levels of granularity. For long-distance routing, we can jump across higher-level tiles before zooming in to street-level detail, significantly speeding up the computation. Storage needs. Storing all the map tiles, especially across different zoom levels and in multiple versions, e.g., for real-time updates or different visual styles, is incredibly data-intensive. At Google's scale, we're talking about over 100 petabytes of map tile data globally. This data is distributed and replicated across data centers for availability and performance. Let's walk through the high-level architecture of a system like Google Maps, which integrates multiple services to deliver real-time, accurate, and visually responsive map experiences to users. 1. Location service. The client device, such as a smartphone, continuously collects GPS coordinates and sends location updates to our backend. To optimize network usage and reduce power consumption, clients may buffer updates and send them in batches at regular intervals. Given the massive volume of location data coming in from millions of users, we use a write-optimized database like Cassandra to handle high-throughput insert operations efficiently. We also integrate Kafka as a stream processing backbone. This allows us to build downstream consumers for analytics, real-time alerts, or traffic aggregation without impacting the core ingestion path. The communication protocol between clients and servers is HTTP with Keep Alive, minimizing the overhead of setting up new connections for each update. 2. Navigation service. Navigation relies more on accuracy than latency. Users can tolerate small delays in route recalculation, but they expect the system to be precise in guiding them through the streets, turns, and exits. Our algorithms must continuously match noisy GPS signals to road segments. This is known as map matching, and recalculate routes dynamically based on real-time conditions. 3. Map rendering. On the visualization side, map rendering is handled through map tiles, which are small square images representing a portion of the map at a specific zoom level. These tiles are fetched on demand, based on the user's viewport, i.e., their location and the zoom level they're currently using. To ensure fast and scalable delivery, we pre-generate map tiles at different zoom levels and distribute them globally via a Content Delivery Network, CDN. This minimizes latency and ensures that users can smoothly pan and zoom around the map. Overall, this high-level design allows us to deliver a seamless, responsive, and scalable map experience, leveraging real-time location data, efficient navigation algorithms, and optimized map rendering through tiling and CDN caching.
Let's take a closer look at the core systems and optimizations that power Google Maps at scale. 1. Data model. At the heart of map navigation is the routing tile model. Each tile represents a geographical area and stores a compact graph with nodes, intersections, and edges, roads. This allows for efficient route computation and incremental updates. In addition to routing tiles, we store user location data for real-time services and historical analytics, geocoding data to map addresses and place names to GPS coordinates, pre-computed map tiles at various zoom levels for faster rendering. 2. Location service. For storing high-volume location updates, we use a key-value database. Key, a tuple of user ID timestamp value, the corresponding latitude-longitude pair. This format makes it easy to retrieve a user's movement history or the latest known location. One key optimization is using vector data instead of raster images for map rendering. Vectors define paths and polygons that are interpreted and drawn by the client. This approach reduces bandwidth and improves clarity, especially on high-resolution displays. 3. Navigation service. This service is composed of multiple microservices working together. Geocoding service converts addresses into latitude-longitude coordinates and vice versa. Route planner determines optimal routes based on graph traversal and traffic conditions. Shortest path service underpins route planning using algorithms like Dijkstra or contraction hierarchies. ETA service estimates travel time using real-time traffic, road conditions, and historical data. Ranker service ranks alternative routes by various heuristics, speed, simplicity, or scenic value. Updater services periodically refresh route and traffic data based on new telemetry and reports. 4. Delivery protocols. Different user interaction models require different delivery methods, push notifications, for alerts like traffic accidents or arrival at destination. Long polling, useful for fetching updates where persistent connection isn't feasible. WebSocket maintains a bidirectional connection for real-time updates such as live location sharing. Server-sent events, SSE, Lightweight, unidirectional streaming for use cases like live traffic overlays. This deep dive shows how Google Maps balances data complexity, performance, and real-time responsiveness. The architecture is modular, scalable, and optimized both for mobile performance and global reliability.